Hello everyone, how are you? Did you miss me? Not much? Yeah. Did you watch the lectures? Okay, so you're up to date. So I was on travel last week. I don't think I told you why I was on travel, so I will tell you, even if you don't care, I will tell you about my trip a little bit and why I'm so exhausted today. So I'm not going to teach any new material today. I gave you the homework ahead of time. I decided I'll give you 3+ days in general. This was one of the comments from last year, and also Patrick suggested at some point to give a little more time than a day. It really, all these homeworks should not take more than a few hours, in my opinion. If you develop the uncollected ones by yourself, if you are up to date with the videos, with the lectures, you should be able to do it very quickly, but you know, it doesn't make any difference. It's only 5% of your grade, and once again, just sit down and do it by yourself. It's pointless if you don't understand what you're doing, because then you will have to do something similar, not in MATLAB, but very similar during the tests, which are much more than 5%, as you know. So this is up. It's due, when is it due? February 2nd? So we'll discuss it today. So where I was this last week was, I was in Italy. I was invited to be part of 2 PhD committees for 2 students at the Polytechnic of Milan. I have some colleagues there. So they invited me to attend their dissertation. Pretty nice work. One guy developed control algorithms to land on any heavenly body, the moon, Mars. It's basically an algorithm that is able to detect dangerous areas and then retargets by itself. And then another one, second one was really impressive, worked on debris removal strategies. And one of them was, you probably have seen these already, but basically throwing a net to a piece of debris, grab it, and then with a cable just tow it to a different orbit. And it was really impressive because the guy modeled everything in, with equations and numerical simulations, and then they actually did this test on those Vomit Comet experiments, the European version of the Vomit Comet, and the experimental results really matched what he had on MATLAB, which is really amazing. So not only he modeled the net and how it wraps around the piece of debris, they also developed control algorithms to trust with the towing spacecraft, so that of course you don't collide with this object once you have it in tow, because you have to do it carefully, right? The cable is flexible, and it can go back and forth. So very nice work. But my trip was terrible. I got there because of cancellations of flights the morning of the defenses. So I just landed, went, attended the defenses, and then I had a train to Rome to go meet some colleagues the days after that. And same kind of story yesterday. I flew back through Atlanta, canceled the flight. They didn't cancel the flight. They started delaying, 1 hour, 2 hours, 3 hours. I have zero trust in airlines these days. So I just rented a car and drove back. So I was back at home like at 1 in the morning, jet lag, so I'm done. So I can only discuss a homework. If I try to write equations on the board, it will be a mess, probably. So be patient with me. And also, at this point, I really can't change. I don't plan any more trips where I'll give you old videos. So I was going to change anyways a few things that I'm going to do from next time. So at this point, we will see the Kepler's equation, not today. So it will be probably a very short meeting today. But the Kepler's equation is what will relate the true anomaly with time, which is what we are missing at this point. It's an equation that has to be solved numerically. And so in the past, I would demonstrate all the steps to get to that equation, which is really algebra, a little bit of geometry. There's no real dynamics behind it. So I decided I will compress what used to be 2 or 3 lectures into one and give you the key points, the things that you need to know and be able to use, so that hopefully I'll have more time to cover other topics during the semester. So I'm just reorganizing things and decided how much time I want to spend on actual demonstrations or new concepts. And it's always good to know where the demonstrations, where the formula comes from, but you won't be able to demonstrate everything anyways. So the homework. Do you have any questions about the lectures that you watched, by the way? Are they pretty clear? So everything in this homework is related to, how do I do full screen? I don't know. Here it is. Everything you see here has to do with what has been done up until the videos you watched. Can you read these? So, oh, it works. Nice. I didn't know that. Good. Okay, so this is one thing that also I didn't do last year, and probably it's a good exercise to go through these guidelines once and for all, so that we are all on the same page. This is a page that you will see at the beginning of the tests as well, so let's just read it together once and for all. So this is valid for homeworks and tests. I really do not care. You can use any books, personal notes, electronic aid, Google, Wikipedia, whatever you want to use, as long as it's correct. But what I care about is that you find the material by yourself. So don't get any help from anyone, because that's the process of learning. It's also finding the information you need, even if it's just in your notes. You need to know what it is that we're talking about. And from this point on, even though I moved office hours for today to tomorrow, which has to do to the fact that I'm extremely exhausted, you cannot ask any questions about the homework to me or the TAs, but we can talk about the topics that we have seen in class. So if you have questions about the videos you watched last week, you can definitely ask me tomorrow, as long as you don't ask me a specific, solution for one of the points that we will see. But there's office hours tomorrow, but don't ask for help from this point on. You should be able to solve it by yourself. And, well, don't cheat. There is no way for us to say if you're really collaborating on the homeworks. And, I don't necessarily care, because it's only 5% of your grade, and if you just copy it entirely from someone else and then you show up at the test and you have 50 minutes, you don't even know what an eccentricity vector is, and you spend 25 minutes just finding the page in the book, that's on you, because you didn't do this. So I'm sure you will try to solve it. So, okay. Guidelines for your solutions. Some of these really affect what you will do during your test, not necessarily the homework. We need to understand what you write. What you turn in is the product of your work, and presentation of your work is important. If it's not legible, if it's not understandable, it's nothing. It's like you haven't done anything. So we will not decipher sloppy handwriting, which again doesn't really apply to this homework, because as you will see, is basically MATLAB code only. But if we don't understand what you write, we don't read it. That's it. For in-class exams, everything must be handwritten. So I've had people, I don't know why, in 50 minutes they turn in weird stuff that is not their handwriting. And even during the homework, they would scan pages of books. I've seen all sorts of strange stuff. Just give me your code and give me your pieces of paper where you actually wrote something. That's all I need to see. No software, no scans. Just your handwriting. This is for in-class exams. If there's anything else that appears there, 0. I hope it's clear. And so, especially for exams, if there is more than one step, if it's just a formula you have to apply to find the number, great. But if there are more steps, just be clear in explaining those steps. If you make assumptions, be clear in explaining those assumptions. Because if there is more than one solution or more than one assumption that I can see in your solution, I will just pick the wrong one. So this is just so that we understand. Clarity is paramount. It's very important. So also, don't forget your name or UFID. I mean, that's not uncommon, that people turn in a test and we don't know who they are. And that's a problem. So in short, write your solution in an orderly fashion so that somebody else, which is us, can make sense of what you're doing and saying. Please be aware of this. This is a very difficult thing to do, but as engineers, you will have to do this more and more during your career. You need to always think about the fact that someone else is going to look at your work, not just yourself. You can understand what you're writing down, but what if you write it today and then you pick it up in a month and you don't understand it? That means that someone else will not understand it. And that happens more often than you think. If a relevant concept is applied properly, then we give credit. But if you apply incorrectly a concept and you get the right number, I do not care. The concept is applied incorrectly and you just had some luck. Okay? Pretty simple stuff. But I wanted to go through this, and there is this honor code signature here that is really, for the homework, the only page that maybe you want to scan and turn in as well. Everything can be uploaded on Canvas, by the way, for your homework. How do I go back to, of course, like this? So you can upload as well the signed page. Okay. Here is your homework. I'm not going to give you the solution, just go through it, of course. It's due on the 2nd at midnight, so you definitely have more than 3 days. 100 points spread around. The following requires you to turn in working MATLAB files that we can run without errors. So that means that if your solution is a main MATLAB file that calls other functions, you need to turn in those functions too. Lots of people last year turned in the main file without the differential equation that would be integrated by the ODE45, the function that implements that, for example. I want a product where I download your files, I run the main one, and magic, all the plots come up and everything is working. So don't forget files. Don't just turn in the main file, please. So these files should output whatever we're asking here, quantities, plots. You can upload on Canvas, of course. Okay, so this is what we're asking you to do, which should be absolutely no secret if you are up to date with the lectures. So we're giving you here a perigee and an apogee, 10,000 and 30,000 kilometers. Those are the radiuses. You need to find the eccentricity, same major axis of this orbit, its orbital period, its velocity at those points, perigee and apogee, the specific angular momentum at perigee and apogee, which I'm sure you're already thinking what they are in terms of their relationship, and that's exactly the question we're asking you here. How do they compare? Pretty simple, right? It's all, these points here are in particular, except the angular momentum, which we did a long time ago at this point. It's all from last week, those 3 videos you watched. This is something we have done in class, actually. So it should really be not a big deal. ODE45, with those options, the maximum step of integration is 10 seconds. Maybe that's too high. Take the equations of motion and integrate them for one orbital period. Of course, we're talking about the basic Keplerian orbit, r double dot minus mu over r cubed r, nothing else. Just ideal orbits. Time step of 10 seconds max, and plot the trajectory in ECI XYZ with a red line of a certain width with those initial conditions where the position of the satellite is purely on the x-axis and the velocity is pointing at that position, which is the perigee on the y-axis. Just in equatorial orbit, as you can imagine, because you are sitting on the xy plane and the velocity is also lying in that plane, so it will stay in that plane, right? If you get something else, there should be a warning that something is wrong in your integration. And then uncollected homework 1 right here, using the alternative to integrating directly the equations of motion, use the parametric solution for Keplerian orbits, where the parameter is the true anomaly, to obtain the position vector. So I'm not asking you anything about velocities here. Every 1 degree of true anomaly. So this is pretty much uncollected homework 1. And you plot what you get from this approach on top of that figure, the same one, and just validate with a different line in black, and validate that they match, which is what we're asking you. So no surprises. Now here we repeat the same problem right there by modifying the initial conditions to now have still a circular, an equatorial orbit, and I'm specifying just in case that means xy plane, but I want it circular, with the same major axis as problem 2. So I don't know what you will get there, right here. Whatever it is, it's probably not circular. So you need to change something to obtain the same major axis, but have a circle. Okay? So that requires just a tiny bit of thinking. What is the condition to get a circular orbit? Go back to your videos from last week. So these 3 days will give you also time if you haven't really watched those videos. Now you really want to watch them. And then same those 3 videos. What is the minimum velocity required for the satellite in problem 4 to escape the Earth's orbit given its same initial position? How do you escape? What kind of trajectory do you need? Parabola, okay, so that should basically give you the answer. There is a specific condition that parabolas verify in terms of velocity. So once you modify what it is that you need to modify your initial conditions to get that, then you plot that parabola, hopefully, over the same time span as problem 4, which is 1 orbital period. So whatever is the orbital period of problem 4, just use it here. Using a different line, green, with 2. And what type of orbit it is, we already answered that, but verify that that's the case. And then a few more points, if you need them, is finding the difference in orbital specific energies between the trajectory, spacecraft trajectory, in problem 4, which was asking you to do a circle, and the spacecraft in problem 5. What is the energy on a circle? What is the sign of the energy on a circle and an ellipse? What is the sign or what is the value of the energy on a parabolic path? No idea? Go back to those videos. Go back to your book. It's in the book as well. So there's nothing hyperbolic here, but that's all you have to do. It should be more than doable in really a few hours. Does it make sense? Is it more than you expected? No. Okay.
You want us to all this in MATLAB, or including comments for the explanation answers?
You can really turn everything in MATLAB. Even if you really want to be thorough and answer this question and actually say parabola, you can do a print screen in MATLAB. You can write a line of code that says text parabola, trajectory is a parabola, so you can print it in the workspace, so you don't have to actually scan any piece of paper or turn in anything else other than MATLAB.
And comments are fine too.
Oh yeah, that's a very good point. Those percentage symbols and then words that you see in the MATLAB files that we develop, those are comments, and they're very, very useful. We look at them as well. So you may forget to print on the workspace that is a parabola, but maybe you are actually writing it in the MATLAB code. That counts as well. We may miss it, but if we miss it, then you come back and we'll look at it again. But comments are absolutely fine as part of your deliverable, in the code. Strongly recommended. Otherwise, you go back to your code and you don't remember what it is that you're doing. Yep.
Can we use part of your example code that you uploaded?
Whatever I gave you, you can use it. So if I go back to right here, you may use resources as long as you just find them by yourself. You would be surprised how many people didn't know that there was a lot of code available that I developed and posted last year, and they were just reinventing the wheel. Just didn't know that it was there. Sometimes it's just a matter of knowing where to look, really. In your book, in Canvas in this case. Any other questions? Was way too short for you? I can start what we'll do next time if you don't have any other questions. I can try to start. You good? All right. Just a few minutes. I'll just give you the start of this. Okay, so this is really in the syllabus, I think this is called as orbital position as function of time. So just to refresh where we are, we said a few lectures ago that we have two vectors, h and e, that are constant, that are also perpendicular to each other. And so by themselves, they would give me six constants for the motion on ideal Keplerian orbits. But the fact that there is this relationship, it actually tells me that it's 5. And then based on that, we found the solution for the position and also for the velocities that I'm not going to use now, but the parametric solution for the trajectory in this form. And then we said, for now, I don't care about time. I just have this angle that goes from perigee at 0 and goes around, and I replace time with this true anomaly. So at this point, we may want to find a way to connect, to basically bring back time into the picture, right? Because for now, I can tell you where a spacecraft is as a function of true anomaly, but not really as a function of time. Okay, so we start from this. If you remember, h is rv perpendicular, which is also equal to r squared theta dot. Oh, wait, people don't erase the board. And which also means that theta dot, which is d theta in dt, is h over r squared, which if you take that expression for r, square it and substitute the denominator, you get, let's see, mu squared over h cubed, if I just simplify right away, 1 plus e cosine of theta squared. Which leads to, if you separate the variables here, to this equation. Let's see, mu squared over h cubed dt is equal to d theta over 1 plus e cosine of theta squared. Agree? So that is your equation, differential equation for now, that does relate true anomaly and time in general. So I haven't made any assumptions here about the eccentricity. It could be 0, it could be 0, between 0 and 1, could be 1, above 1. That's very generic. So this is what I would do. Well, let's go one step further actually. Let's do this. If you integrate that both sides, this is what you get. Mu squared over h cubed, and say that you integrate from perigee, so I call t at p whatever is the time at perigee, that you can assume is 0, of course. This will be equal to the integral between 0, that's the true anomaly at perigee by definition, and a generic theta value for that function there. E cosine of theta squared. I said I wasn't going to write any equations, but I am. We'll see. We'll see what happens. So yeah, we can assume this is 0. This is usually what we do. And so you have mu squared over h cubed t, which is equal to this integral here. Now, this is the part where I will skip a lot of demonstrations because I don't think they are necessarily that beneficial, and we really are not going to use them during the rest of the semester. So that integral there does have known solutions, and it depends on the e value. So what I would do is write on the board these very long expressions for the solution of that integral on the right hand side, depending on the e value. But I'm not going to do that. I'm not going to dig into those steps because, again, we'll just do it once and never use it. So let's do one orbit at a time and look at how you relate how you try to basically solve this equation here. Okay, the left-hand side is solved. It's mu squared over ht. That's done. But these will change depending on E. So we start with the easiest, which is circular, which means E equals 0. Well, there's really not that much to say, right? As expected, is equal to theta. That's your relationship. This is the only case where I said that there is a relationship between theta and time that has to be solved numerically, except for circular orbits. This is pretty analytical. And that is something you should have expected, right? Circle, kind of. Okay. Probably better. We know that if you pick any two position vectors, the area that is enclosed by them has been swept by a certain amount of time, that if you move that everywhere should be the same time. So being a circle here, you really would expect a linear relationship between time and angle, right? Since the radius is not changing, this distance between M1 and M2 is not changing, right? R is constant. I think that's something expected. Now, since we also know that this R is h squared over mu, if you combine these two, you can say that T is, I'll just give it to you, R 3 over 2 to the power of 3 over 2 over square root of mu theta. You see that? T is h cubed over mu squared theta. I want to make R appear here somehow. This is what I get. Remember that the orbital period is, this is something you should have seen, is this expression. You would have A here in general, right? For an elliptical orbit. This is also what we call the one of the Kepler's laws. The relationship between period and semi-major axis that collapses into radius for a circular orbit. So if I use that, I can rewrite also that T is equal to period over 2 pi theta, or otherwise that theta is equal to 2 pi over period T, which is a lot of playing with formulas, but I could have just written that right away, right? Think about what it is that it's happening here. You're just moving with a point on a circle at a constant speed. This is angular velocity, if you want. It's 2 pi over the orbital period. It's the entire angle going around once over the period. So that's kind of expected, right, for a circle. Is this clear? So this is the only case where this is really a no-brainer, direct relationship. So I think I'm going to stop here for today. Sorry, guys, but I will compress everything else, elliptical, parabolic, and hyperbolic, next time.